How many slides do you have?
Today we have, I think it's 8, but they are. This section is mostly review, so it shouldn't take too terribly long to get through. Okay, so I'll kind of just read through it and just kind of see where you're at on the copying down, then we'll proceed. It's going back again. We're still on the periodic table, but it's going to be referencing our last chapter and just, talking about how it's organized by electrons and stuff like that. So, might as well get started. So when we are discussing elements and their unique physical and chemical properties, it all kind of boils down to the electrons themselves, and more importantly, the valence electrons. And the valence electron, if you don't recall from last chapter, is defined as electrons in the highest principal energy level of an atom. When we're looking at the periodic table and we pick a specific group, or remember a vertical column, the individuals in that same vertical column are going to have the same number of valence electrons. And as I mentioned, the valence electrons are really what provide the properties for the elements. This means that the elements in the same group are going to have the same or similar chemical properties. Again, we have the example here on the slide of group 1. Okay, hydrogen, as a reminder or a refresher, pop quiz type thing, let me remember what the name of the elements in group 1 is. From section 1. What do you think?
Representatives?
They are considered a representative group. They have a specific name, though. Starts with an A.
Alkali?
Alkali metals. So group 1 is known as the alkali metals with the exception of hydrogen, but hydrogen still has the same number of valence electrons. But as you see here, lithium, sodium, potassium, rubidium, cesium, francium, all members of group 1 are going to have 1 valence electron, as indicated by the electron configuration there. So we can also look at valence electrons in terms of the period, the horizontal rows. And so since we mentioned what a valence electron is in terms of their energy level, the energy level of an element's valence electrons indicates which period on that table it can be found. Again, using lithium as an example. Its valence electrons, or electron I should say, and I'm going to go back to the slide. Its valence electron is in 2s. Lithium is found in period 2. Gallium, which is all the way over here, just past the transition metals. Okay, its valence electron is found in the 4th energy level, in 4p1, and 4s1, or 4s2, and 4p1. So it is in the 4th energy level. So we can use electron configurations to not only tell us the number of valence electrons, but where the element itself can be found. So we can, just by simply looking at the periodic table, help us determine the number of valence electrons that there are for each element. And we use these representative groups, or the groups that in the S and the P blocks. For groups 1 and 2, so the alkali metals here and alkaline earth metals, their number of valence electrons refer to their group number. Alkali metals are group number 1. The alkaline earth metals are group number 2. Now, as we hop across the pond and start over here with, say, boron, okay, the number of valence electrons for those elements, which are most of the time they're labeled as groups 13 through 18, are going to be 10 less than their group number. So if we look at helium's the exception because helium can only have 2 electrons maximum. But another way we could think of it, so boron, which is in group 13 right here, if the number of valence electrons it has is 10 less than the group number, that means boron has 3 valence electrons, so on and so forth. However, some periodic tables are simplified, meaning that they'll just go ahead and call these groups right here, groups 3, groups 4, group 5. As you can see, if you're able to see on this periodic table, they're in Roman numerals. Okay, so you've got 2 different ways to help make predictions on the number of valence electrons for elements. Now, that's for the S and the P blocks. Okay, when we get into the transition metals that are right here in the center, all of those elements are going to have 2 valence electrons. And we can refer to the electron configuration to help us with this. Because let's say we're over here and we look at vanadium right here. Okay. Obviously, it's in transition metals. It's in the D block.
You need to get a textbook.
Oh, boy. But what do we know? If we're doing the electron configuration, the vanadium's right here. This would be 4s2. Okay. What happens when we go down here to the D block? What number does that turn to? 3. Very good. But the valence electrons, as defined a few slides ago, are the electrons in the outermost energy level. So all of the transition metals are going to have, excuse me, an S2 electron configuration as part of their overall configuration. So that's why we have these transition metals going to be all consisting of 2 valence electrons. So here's where we get to our reference back to last chapter. Okay, as we've seen and talked about quite extensively, that the periodic table is broken up into 4 blocks. Okay, the blocks on the periodic table are organized in columns and rows of varying sizes, which represents an atom's energy sublevels that are being filled with these valence electrons. And that's why we have this kind of weirdly shaped table, is all because of how it is arranged based upon the energy sublevels. So we've got the S, we've got the P, we've got the D, we've got the F. Again, I've already mentioned here before when we got to this slide, 3 out of the 4. So as you proceed down the periods of the table, you're going to see an increase in the principal energy level. So what that means is the number of energy sublevels containing electrons is also going to increase. Period 1 contains only S block elements. That's going to be hydrogen and helium. Periods 2 and 3 contain both the S and P block. Periods 4 and 5 contain the S, P, and D. And then lastly, periods 6 and 7 contain all 4 S, P, D, and F blocks. So let's look at these 4 blocks individually again as a nice little refresher. The S blocks contain groups 1 and 2, so the alkali metals and alkaline earth metals. With these elements, we have valence electrons only occupying the S orbitals. And the S orbital, or S sublevel, only has 1 orbital. And each orbital can only contain a maximum of 2 electrons. Therefore, the S sublevel can only have a maximum of 2 electrons contained within it. P block over there to the right contains groups 13 through 18, or depending on which periodic table you're going to look at, contains groups 3 through 8. You don't encounter the P block until period 2. And with these elements that are located in the P block, you're going to have valence electrons in both the S and the P orbitals. We first fill the S orbitals, then continue on to the P orbitals. And the P sublevel contains 3 orbitals, again, with each orbital only having the ability to contain a maximum of 2 electrons. The P orbital, therefore, can hold a maximum of 6 electrons. And so, what that means is we really, for any element, there can only be a maximum of 8 total valence electrons. And noble gases are those elements that are the only elements that are going to have that. So the noble gases, which are group 18 or group 8, again, excluding helium. Helium is considered a noble gas, but it does not, it cannot have 8 valence electrons. These noble gases have electrons that are going to fill the outer S and P orbitals, so we have a maximum of 8. And so when you have a maximum of 8 electrons as your valence electrons, you're going to have a stable atomic structure. And so when you're stable in the atomic world, you're pretty much not going to have any reaction with any other substances. Again, which led to why they were discovered last. The D block contains groups 3 through 12. Okay, we encounter these elements first in period 4, and it spans 10 columns on the periodic table. And as we mentioned a couple of slides ago, that the valence electrons for all transition elements are going to be found in the S block. The D sublevel consists of, the D sublevel consists of 5 orbitals. Again, each holding a max of 2, therefore a total number of 10 electrons. The D sublevel, I can't even talk today. The D sublevel fills in the prior energy level. So again, if we look at scandium, its highest energy level is the 4th energy. However, the D sublevel is going to fill the 3rd energy. That's where we get that N-1 that we discussed last chapter. And scandium is the first element in the D block in the 4th row. So that 1 electron that's going to fill it after it's filled is going to be in the 3rd energy level. And lastly, told you to be relatively quick today, the F block. These are called the inner transition metals. We encounter the F block in period 6. This time it spans 14 columns. Again, much like the D block, the F block is going to have its valence electrons also located in the S orbital. The F has 7 orbitals, each with a maximum of 2, therefore a total of 14 electrons. And in a similar manner to the D block, the F sublevel is going to fill 2nd prior energy level. So cerium, again, its highest energy level is the 6th energy level. That's where you'll find the valence electrons. But as you fill in the F sublevel, it'll be in the 4th energy level. So nice little review over what we discussed in chapter 5. Again, make sure that all of these are completed for tomorrow's homework check. What's that?
Tuesday I woke up, I was like planning on just like basics, I just